Hello and welcome to Lecture 4 of Magnetic Interactions in Phys 1204. In the previous lecture, we finished off looking at forces on current-carrying wires that are exerted by magnetic fields. In this video lecture, we're going to take that and use it to figure out how the forces on individual moving charged particles work. We've seen that we can find the magnitude of a magnetic force on a wire using this expression. One thing to realize is that this force only acts on the wire if there's a current in it. And so apparently this force must be on those moving charged particles in the wire. So that suggests that we can use this to figure out what the force is on each of those moving particles. So since we know how to write the current in terms of other things, this will allow us to do this. And I'll just remind you that in this expression for the current, the Q is representing the charge per charge carrier. So if these are electrons, then that Q would be negative E. And that little n is the charge carrier density. So let's now put those together. And it gives us an equation that at the moment looks like gobbledygook. But if we just rearrange things a little bit and look at these things at the beginning and notice that LA would be the volume of the wire, and that's being multiplied by the charge carrier density, which is the charge carriers per unit volume, and so LAN is the total number of charge carriers that are moving in the wire. So with that, we can rewrite our force on the wire using that N, the capital N, which represents the total number of charge carriers that are moving in it. And now if you want to know the force that is on each of those charge carriers, you just have to divide that by N, which just gets rid of the N. And so here is the magnitude of the magnetic force acting on a single particle in the wire. Well, there's no reason that this should only apply to particles that are moving inside a wire, and indeed experimentally you can show that this is true whether the particle is in a wire or not. And this is the magnitude given the sine theta in this expression, and that we know the magnetic force on a wire can be expressed in terms of a cross product. You might suspect that this one can be written in terms of a cross product, and indeed it can. So in full vector form, here is the magnetic force on a moving charged particle. Notice that because it's a cross product, as we've already seen, if the velocity vector and the B field vector are in the same direction, then the magnetic force must be zero. And also, the magnetic force must be perpendicular to the velocity, and it must also be perpendicular to the B field. So practice your right-hand rule and verify that for this charged particle in this diagram, the magnetic force must be out of the screen. We're increasingly seeing that there must be some sort of a deep connection between electricity and magnetism. After all, moving charged particles produce magnetic fields. We've seen that currents produce magnetic fields, and moving charged particles also feel magnetic forces. And so it makes sense to start talking about electromagnetism, and so I will increasingly use that term as I'm talking about all of these phenomena we're looking at. So we can write down the total electromagnetic force acting on a moving charged particle, and it will simply be the electric force plus the magnetic force. And we know expressions for both of those, and it's often convenient, since both of those forces are proportional to the charge on the particle, to factor the charge out and write this force this way. And this often gets referred to as the Lorentz force, but all that's meant by it is the total electromagnetic force. In general, the total electromagnetic force on a moving particle is a little too complicated to be reasonable for us to look at in this course. We will look at some special cases of it, but for the moment I'm going to focus just on magnetic forces on charged particles. So notice, as I've already said, the magnetic force is always perpendicular to the velocity. Well, there are several things we know about forces acting perpendicular to the velocity. A force that's acting perpendicular to the direction that a particle is going does no work. And one thing that tells you is that it causes no change in speed. So if the velocity vector is perpendicular to the magnetic field, as in this diagram, we get an interesting special case. Verify for yourself that the magnetic force on this particle is towards the bottom of the screen. So at this instant, this particle is accelerating straight down. As it accelerates straight down, that's going to change the direction its velocity vector is pointing, but the magnetic force remains perpendicular to the velocity, and so it has no effect on the speed. And so some short time later, it will be going straight down at the same speed, and the magnetic force will still be perpendicular to the motion. And a little after that, it'll be going back the other way, and so on. Well, we've seen this. Notice that it's going around in a circle at constant speed, with the acceleration always perpendicular to the velocity. The speed is constant, and because both the speed and the magnetic field in this case are constant, that means that magnetic force has a constant magnitude, and so the magnitude of the acceleration is constant. Well, this is a familiar sort of motion. This is uniform circular motion. And so whenever a charged particle in a uniform magnetic field is moving perpendicular to the magnetic field, it always moves with uniform circular motion. So this is a familiar motion, and it's easily analyzed. We can write down the equation of motion, and note that that magnetic force is given by QV cross B. And if we just realize that this acceleration is always perpendicular to V, it's easy to know which way that is at any time. And so let's just focus on magnitudes. V and B are perpendicular to each other, and so the sine theta in that cross product just gives 1. And now the acceleration magnitude in uniform circular motion is just v squared over r. And so this gives us something we can rearrange in various ways. It often gets rearranged in textbooks to solve for the radius of the circle, but more generally, just note that this gives you a way of measuring various things. If you can get a particle or a group of particles going at a known speed in a magnetic field, then you can probably rather easily measure the radius of the circular path they travel in, and that will give you an indirect measure of the magnetic field strength. Or, if you know the magnetic field strength, you can use this to find out how fast some charged particles are going. One application of this is a device called a mass spectrometer. And this is used a lot by chemists and by others. You can take some sample and split it up into lots of charged particles, which you accelerate, usually using electric fields. And you take that beam of charged particles and run it into a region with a magnetic field. And the magnetic field is perpendicular to the direction that the beam is going. So the particles are going to go in circles in here. And so what that means is that for particles coming in this drawing, you can verify that the positively charged ones are going to accelerate up at the instant they enter the B field, and the negatively charged ones will accelerate down, and so they will go in circles like this. Also note that the radii of the paths they follow is directly related to the mass over charge ratio. Well, that is diagnostic. Each ion has a well-known mass-to-charge ratio. And so you can use this to figure out what kinds of ions are in the beam of charged particles, which tells you what your original sample must have been made of. This is why this is such a useful experimental technique for chemists. I'll probably put an assignment question using a mass spectrometer on the next assignment. here's another useful device where we use a magnetic field to steer moving charged particles in the direction we want. Let's suppose we have a beam of particles, and perhaps you are wanting to feed this beam of particles into something like a mass spectrometer. But note that for a mass spectrometer to be useful, you need to know how fast the particles are moving. And generally, when you make a beam of particles, it can be difficult to make sure they're all going at the same speed. So what we would like is sort of a filter that filters out everything except particles going at the speed we want. And here's how you do it. You use an electric field and a magnetic field. So we're going to be looking at a total electromagnetic force. So let's suppose that the electric field in the region that we're putting this beam through is up. So think about if we want a magnetic field pointing in some direction, so it is possible for the magnetic force on these particles to exactly cancel out the electric field. So this is going to be the end of this part of the video. In the second part of the video, after you answer this question, we'll continue on. So here is the question. For the magnetic force acting on these particles to be able to cancel out the electric force, which way does the magnetic field need to point?